move on to the panel? Should we do that?
Yeah, that sounds great.
Excellent. I see a thumb. Good. Okay. So yeah, really enjoyed all the talks. Thank you, all three of you, for really excellent talks and also quite different perspectives. I have a list of questions, but I'd really just like it to be kind of a free-form discussion, and I'll pipe in with questions if things start to lag. I'm gonna start off with a question for Shuran, and then anybody else can please chime in. Shuran, I mean, your talk was so powerful. Just the complexity of the problem you're trying to solve is amazing, and the fact that you're getting the results that you're getting it's really amazing. I'm curious, in your work, you've combined elements of physical modeling with learning directly from data, and I'm curious if you can, you know, kind of talk a little bit about how you feel, what's the best blend between learning from data and using physics-based modeling?
Okay, so can you hear me?
Yes.
Okay, cool. Yeah, I think that's an excellent question. And I think, frankly, I don't have a good answer for that. I think I tried different versions of combining like physics-based models and data-driven models. I think in particular, something I didn't talk a lot about in this workshop, which I mostly focus on perception, but once we consider like handling dynamics of the objects, like especially like dynamics of deformable objects, it's actually really hard to like simulate accurately. So I think in those cases, like really like learning from data is a very powerful way to go forward. But still, I think there are something that we can leverage, like a physics model that we should leverage, and so that it can be more generalizable. So yeah, I think that's still like my like core research question that I'm still like thinking about every day, like how to combine them. Yeah.
Do you think we need to simulate the dynamics accurately? It seemed like when you were simulating the folding under the force of gravity, it didn't really have to be, am I wrong? Did it have to be very accurate, or could you tolerate a bit of uncertainty there?
Yeah, it also depends on the end application. I think when I show the results and it fall under the gravity, it looks really good. But if you really want it to be like very accurate, so for example, in our paper, we cannot measure the altitude distance from the estimated surface and the simulated surface. It actually always produces higher error compared to if we just use the data-driven approach. But if you look at the data-driven approach, the result actually doesn't look that good. Like sometimes it's like it has self-penetrations, it doesn't look physically possible. So yeah, so I don't know, like I guess depends on the application, you may want certain properties. So I guess ideally we can have like a take best from both worlds, but right now it's just like kind of we just understand the trade-off, but still haven't have a good solution.
Yeah, super interesting. Angju, what do you have to add on this? How do you see physical simulation coming into your work, or have you thought about it from that context?
Not so much about physical simulation, but I am, all for physics-based, inspired models. Like we kind of, appreciate that, or accept it as given. I think it's a fine inductive bias to give as long as you kind of go over it. Yeah, in these kind of reconstruction worlds, I think the interesting thing is like Nerf really bakes in the appearance in these fogs, and like what if you wanted to know like the light directions, or like you can also be doing more inverse graphics like things, and so solve explicit for surface normals and like light directions and all of these things. That's kind of interesting. But I think it's like I'm curious about Sharon's kind of like closed folding problem, because like I wonder if it's like this is something somebody else was asking about canonical versus object space, or canonical or not. Clothing is hard, but it's also kind of, if you focus it to be like a folding problem, do you think like what canonical space is best? It's actually a really interesting domain. Is there any, or there shouldn't be any, or like, it's like, do you think there's enough data to learn something on this? I mean, I guess, aside, but like in real life, from images data, not from like, synthesized cloth.
Andrew, I'm getting the feeling that you really want Sharon to make you a closed folding robot.
Yeah, I get that. We are actually working on it. I'm promise you. Okay, so let me highlight some challenges of like thinking about folding cloth, right? So we work actually a lot of work on like unfolding clouds. It actually works pretty well. It's actually much easier. But once you start to think about folding clouds, one of the first challenge we face is how to define the goal conditions. So especially if you think about it as a category level. So if you have one class and only thinking about folding one T-shirt, then it's probably easy. Like you can do demonstration, you can define the full configurations or key points. But if you want this manipulation strategy to slightly generalize to different T-shirts and garments, and maybe jacket that has like a zippers in the middle, it's actually very hard to like define one goal condition for all of them. So for us, we feel like folding clouds is one task, but for robots, actually, it's really like different tasks when you consider different instances. So that is one of the challenges that we actually facing now. I think we are also thinking about how to solve it. And I indeed working on it. So next paper, maybe I'll have better solutions for that. Yeah.
Very nice.
Along those lines, I'm wondering if you all have seen these YouTube videos of kind of expert T-shirt folders. There's some particular pinch points in a certain pattern where you can grab them in the right way and then just pick up and it's folded.
That's true. Yeah, actually, some of our system also try to get inspiration from that, but still, they actually, if you think about how that system works, it kind of like unfold the clouds first and then find those key points, right? And that key points, again, is kind of defining by like either instances or a category level, like object level. And then, yeah, so I think that makes things easier for like T-shirts, but it still requires some like non-trivial perception task to be solved. Yeah.
Absolutely. Absolutely.
Oh, and another thing is that those manipulation actually typically like leverage dynamics of the class. So if you actually slowly pull those points, it won't fold by like what you'll see in the video.
Interesting.
Yeah.
Interesting. Ransalu, I'm curious, also going back to the theme of physical models or not physical models, in your dynamic occupancy grid work that you were showing at the end, is there physics involved or kinematics or something there, or is it purely data driven?
It's purely data driven, but if you like have a, say, somewhat good physics-based model, then it's possible to incorporate that as the prior, because in my models, like I have the prior. So there's this opportunity of incorporating that prior in the model, but the challenge is like that needs to be represented in terms of probability distributions. So that's kind of the challenge I see.
Right.
Yeah. So for modeling, I haven't like really tried to incorporate like physics-based model, but for decision-making stuff, we have worked on like, say, autonomous driving. So can we basically start with a physics-based model, then try to do more like, so you have black box, white box, and in the middle, we have gray box. Try to do more data-driven learning.
That makes sense. So along the lines of uncertainty, so your focus, I understand, is on representing the uncertainty, which is great. How do you now use that when you're starting to think about action and planning for the robot decision making?
Right. Yeah. So it really depends on the application, right? Say for something like autonomous driving, so we don't need to make sometimes the safest action, right? So we cannot be like really slow just to make the safest action. So we always need to like think about what is much more practical. So if you're driving, what is much more practical? So if you are okay with like, say, whatever, 95% probability, so that's the surface that we are going to query. So that is, then we can actually like look at different probabilities and forward simulate the decision maker and see what the results would look like. So that is kind of the advantage. And then pick. So when picking the actual decision, then there are a lot of things, right? There are ethics, there are safety aspects, there are rules. So those things also come into play.
So I have a question about this. The basic input to this data to compute the uncertainty is like the LiDAR responses that I'm assuming, right?
Yeah, so in my case, it's LiDAR or radar, some kind of depth information.
Some kind of depth information. And then because they're noisy, you're modeling this in an with uncertainty ways, kind of.
Yeah,
right?
so yeah, it captures like the noisiness of data, as well as like in some areas we do not have data, right? It's like for instance, occlusion. So just think about like when we are driving in traffic, we cannot see everywhere. Like most of the areas are occluded.
Right.
So in that areas, we try to predict something meaningful, but it's not sure. It will indicate by the probability.
I'm curious about both Shuran and Angju, how you all think about uncertainty. Maybe Angju, do you want to comment a little bit more on that? In the context of Nerf and 3D scene reconstruction or planoctries or whatever method, where do you see uncertainty coming into play?
I think we don't. I think it often happens in my line of work. It's just like the problem is hard and we can't really reason about the uncertainty. So we always go for the mode. But I think it's interesting. This is why I'm asking about the input is LiDAR, right? Because I kind of feel like you can't treat all of these densities as uncertainties. Or as like uncertain metrics, right? And then kind of get something that is sharper. I think that is a big problem in 3D because in any type of Nerf representations, if there's like noise in the camera or like scene moved a little bit, it's gonna get blurry results. It would be really nice to snap it back to you know, a more clear representations. But then I also think you need, you know, data for what is, you know, the likely surfaces and such, and maybe that kind of 3D data is hard to obtain. But incorporating this kind of reasoning inside while you do the optimization, I think is a really interesting direction. In a sense, I kind of wonder if there's like because it's kind of like a fog model, right? And that you are doing, you know, optimization on each of these fog. And so in a sense, it's kind of the particle filter like kind of approach, even is one way to think about it. I mean, I wonder it's interesting to incorporate it more. Yeah.
I'm wondering if you have thought about a robot-centric 3D scene reconstruction where a robot is in motion and produces one image at a time. And so necessarily you're going to have lots of information on a restricted area and virtually no information outside of that, and the kind of streaming and online aspect of building 3D scenes.
Yeah, definitely. I think this is why I kind of wanted that reusable prior that I am talking about, because suppose you can explain everything like the world as vocabularies of like parts, okay, small parts. And then you have observed a little bit, you know, and then you can probably predict what are the most likely pieces that will follow from that. And so in that sense, like if you make it discretized, it's very easy to model the uncertainty and like actually have non-deterministic predictions. I think that's another nice thing that we kind of do things like that for motion synthesis tasks. I think it would be interesting to incorporate it. I think one challenge is like, how do you actually train such vocabularies? And I think that's where it's kind of becomes interesting. Yeah.
Andrew, actually, I'm curious, is there some work has done like with Nerf and active like next best view estimation? So you kind of estimate the 3D and then you kind of know where I don't know and then kind of move the camera. Like if you have a camera that's installed on the robots.
Yes. Well, so okay, maybe there is some work on this. I don't exactly know, but I've been thinking about this a lot. And I think it's such a really interesting problem because perceptually humans walk around, but like we don't really look. And when we want to kind of make something certain, we actually look and so that's a really interesting problem. But then I'm thinking about it, but unfortunately, I think if you just do it on a tabletop, I think there's like, if you just do it wide baseline enough, like it's a very easy solution kind of thing. And I think you should really try it on like a drone or something. You want to capture like, this campus, and you want to fly to minimize it. I think that would be a really interesting stuff, but like something that's easy to set up on the table. I feel like there would be like like a trivial solution that would just be good. And that's true. Yeah.
A trivial solution that just maximizes the coverage will be pretty good, right? Exactly. But I think if you start to think about like more complex objects, like deformable objects or articulate objects, you need to open the drawer in order to see what's inside, right? Otherwise, the uncertainty is it's pretty high inside the drawer. Or the cloth when it's crumpled, the uncertainty is really high, and you can unfold it in order to see.
You're right. I think Dinesh actually had some interesting works like a long time ago. But yeah, it's something definitely to look into. Dinesh Jayaram, he had this paper where like you predict what it's gonna look like, or like predict the next view. But yeah, I love this problem statement.
Sharon, along those lines, I wonder if you have thought about inferring material properties or flexibility only from images. For example, okay, there's a crumpled shirt on the desk on the tabletop, and a human can recognize that's a crumpled shirt, but the robot doesn't know beforehand if it's carved from wood or if it's made from fabric. So if it's rigid or flexible, right? Do you think about those kinds of problems?
Yeah, I do. I think there are different ways to approach it. One is that if you're just thinking about it as a perception task, you kind of learn some parts about texture mapped to material. I think that's like you can train something like that. But I was thinking it's more interesting to learn it from an interaction perspective. So if you allow the robot to actually manipulate with objects, that it's actually much easier to kind of decode or learn their physical properties. Yeah.
Ooh, oh, I guess I guess what are your thoughts on tactile for that? Or do you mean like, you know, you touch it, or do you like see it?
Yeah, I think touch it and see it is like easy way. You don't need additional cameras, and you can already learn a lot. But I think it's indeed it's so much more powerful if you have tactile sensor, right? Or like something that give you force feedback. Yes, I think that's something very interesting. I'm definitely interested in looking into it.
And is tactile on cloth easy? Because I know there are all these nice tactile sensors, but cloth is so small that it might be hard.
Yeah, it is hard. I think I'm not an expert for tactile sensing, but I think we have some collaborators, and we are really thinking about, like, for example, using tactile to pick up one layer of cloth. So that is something like really hard, and we actually struggle a lot. Like our demo always fail when the robot actually pick up two layers. So yeah, that's something that I feel very interesting and very useful.
There might be another angle here concerning tactile feedback, which is the concept of kind of cross-domain sensory inference, where you can imagine a training set with vision data and tactile data, but then at runtime you only have vision. And I think humans do this very well, right? We can anticipate what a cloth will feel like or what a desktop will feel like based only on vision. We can sort of anticipate touch through vision. And I think that's kind of an exciting idea. I wonder if either of you have thought about that, or all three of you.
Yeah, I think that's definitely interesting. I think in the earlier today's talk, Jiajun actually gave a talk about like the object folder. I think that's a pretty good examples of like having a data set that has all the multimodal data. Maybe during training you have all the modalities, but during testing you can maybe hallucinate other modalities.
Definitely.
Yeah.
Yeah. So what Mac is like thinking about, like we have like kind of a common embedded space, like as human, you know, like when I see Mac's picture, I can think of like his voice, right? Your voice.
Right.
I don't need to hear your voice. Like, yeah, so I guess like, if it is something that we have seen, then it's possible to have that kind of an embedded space. But if it is something completely new, then I'm not sure what human would do.
Yeah, some kind of domain adaptation or some kind of category level inference, right? If you see somebody that looks kind of like me, you might expect that their voice also sounds kind of like me.
Ears never match.
That's right. Yeah, one thing that I'm really interested in also is similarly, Andrew, to the way that you described how the architecture of Nerf works, and also planoctries and planoxels, how you basically spatially index the radiance, right? Like at every XYZ position, there's a kind of radiance function tagged to that XYZ position, which is such an elegant way to put it. And it makes me think you can index other things spatially together with the radiance, right? You can also index material properties or audio properties or whatnot.
Well, yeah, or like, you know, graspability or other things that are important for latent representation for the task.
Right.
So this is actually something I thought about when I first started, so AtlasNet was around the first time I started thinking about these MLPs that can like predict these things properties. It's like kind of like a high dimensional implicit version of a voxel. It's really funny because the research kind of goes in helix because the 3D reconstruction was always voxels, and then we like hated on voxels because it's low resolution, and then we're like, oh, these implicit representation is good. And then when that came out, I was like, oh, it'd be really cool to learn these task specific action enabled interactive like latents. But then the problem was that these implicit functions are way too slow to render, and then you have to get the heat map. Actually, this is very similar to some of Sharon's way of doing things, of like computing this heat map and then picking the one with the highest likelihood. It's just that then you have to query all of these things, and you get into this issue that it's very slow. It's like the original Nerf is super slow. And so I was like, forget this, it's not gonna work. But then now that we have all of these explicit approaches that are faster, I think it's more hopeful, and I think that's a really cool direction. One issue though is that once you go explicit, then you are actually again bounded by memory. But I think there are new ways that are to basically characterize this volume that allows you to store something not super high dimensional, but some not a little bit high dimensional, that like I think that would be a really cool direction to learn it from interaction.
Great. I think that's a perfect place to wrap up our discussion. Thank you, Sharon. Thank you, Angju. Thank you, Ransalu. Really great conversation, and I hope the audience enjoyed it as well. And let's go ahead and conclude the workshop. Preston and Shreyas, do you guys want to say some concluding remarks?
Yep. Yeah. So again, we just want to say thank you so much to everyone who attended. We want to say thank you to all of our fantastic speakers today. I know I've definitely enjoyed the discussion. Yeah, let's have a round of applause actually first. Yeah, so I don't know that we landed on any, particular answers of good representations. Like we haven't solved, I think, learnable scene representations or anything like this. But really our goal here today was to more kind of start a conversation among people in the community of, there's people working on SDFs, there's people working on object level representations, et cetera. And so I think really what we wanted to do is get together and kind of discuss different ways that these learnable scene representations and object representations could be used, concretely in these robotics tasks. And so, yeah, I hope everyone has really felt like, this discussion was productive and this has sparked some, research ideas for everyone. Yeah. So I guess with that, again, thank you all of you for coming. I hope you have a safe trip home. And yeah, thank you so much.
Thank you for the organizers.
Thanks, everybody. Safe travels.
Bye-bye.
Bye.
And Andrew, Andrew is not here. Okay.